So welcome to week 7. I'm running a bit late this week, so the first video is at night. And I want to start talking about adjacency matrices. We've come across adjacency tables once before, so I'll start with one of those. So here's an adjacency table that describes a graph with 4 vertices. It's written, whereas before I did write it as an actual table, this time it's written in sort of computer jargon, but the principle's the same. This is just describing a graph with 4 vertices, and it's telling us that, lots of parentheses and brackets and so on, that's confusing, but it's just telling us that vertex 1 is adjacent to vertex 2, whereas vertex 2 is adjacent to vertices 1 and 3, etc. And it's very easy to draw the graph that satisfies these rules. Namely, we have a graph with 4 vertices which are all in a line. So they're just edges that go sequentially between the vertices like that. So this is vertex 1, this is vertex 2, 3 and 4. You see, if I do that, I'm satisfying all the conditions in this, what is effectively an adjacency table. Vertex 1 is adjacent to 2. Vertex 2 is adjacent to 1 and 3, vertex 3 is adjacent to 2 and 4, and finally vertex 4 is adjacent to vertex 3. So this describes this so-called path graph with just 4 vertices. Now this is a very special, obviously very simple graph. It's an example of what's called a tree. A tree, you've probably seen already by now, a tree is a connected graph with no cycles. So this is certainly a tree, and if a tree has n vertices, it has n minus 1 edges, so this has 4 vertices and 3 edges. Now later in the week we'll be using trees to search graphs. We'll find spanning trees, trees that contain all the vertices of a graph, but without any of the cycles that the graph may have. But for today, I want to link more with the linear algebra. I really want to talk about adjacency matrices rather than adjacency tables. So let me give you an example of an adjacency matrix, indeed for this particular graph. So here's an adjacency matrix. Unfortunately, I've got to draw the graph again. So let's quickly write down the path graph with 4 vertices. So the adjacency matrix is just another way of explaining where the edges are. We have to again label the vertices because each row or each column corresponds to a vertex. So I labelled them again 1, 2, 3, 4, and the you can interpret this matrix like this. If you go to the first row, you can think of that as corresponding to vertex 1, and then the entries in the columns tell you what the adjacent vertices are. So the 1 in the second column just tells you row 1, that vertex 1 is adjacent to vertex 2. Of course, it's also true that vertex 2 is adjacent to vertex 1, so the matrix is going to be symmetric. So this is the adjacency matrix. So the definition is that each entry of the matrix, Aij, it's going to be 1, at least for simple graph, it's going to be 1 if vertex I is adjacent to vertex j. Otherwise it's going to be 0. Because we have a simple graph, there are no loops, so we have zeros down the diagonal, we have no multiple edges, so an entry is at most 1. In fact, when you have the path graph, or even if you have more than 4 vertices, you can see there's a very easy pattern to this matrix. Namely, we just have a diagonal row of 1s below the diagonal, and a diagonal, the principal diagonal, and a row of a diagonal of 1s above the principal diagonal. So that's the adjacency matrix for this type of path graph. Okay, let's move on. So if the graph is not simple, it's a little bit more complicated. We won't be dealing with non-simple graphs much, but you just have to bear in mind that you may have loops or you may have multiple edges. So you might imagine, for example, if we have the path graph again, it's a bit thick, the 4 vertices. Suppose we have a multiple edge. Maybe we have 2 edges going from vertex 1 to vertex 2. Maybe we also have a loop at vertex 1. Okay, so in this case, the matrix would start like this. Because there's a loop at vertex 1, you actually put a 2 in the diagonal position to represent the fact that there are sort of 2 edges coming into 1. The fact that they're connected you don't see. And you'd also put a 2 going from vertex 1 to 2 or from vertex 2 to 1. The rest of the graph, if we don't do anything, would be similar to before. So there would be zeros here and so on. So that's how you deal with the adjacency matrix if the graph is not simple. The interesting thing here is that if you, this is always true for an adjacency matrix, if you add up the entries in a given column, say, in this case you're going to get 4 if you add up the entries of the first column, or indeed the first row because it's a symmetric matrix. The 4 is really telling you that there are 4 edges coming into vertex 1. So it's actually telling you that the degree of vertex 1, so the degree of vertex 1, write it like this, is equal to 4 in this particular case, because we've got this loop and this multiple edge. But it's always true for in the adjacency matrix that the sum of all the numbers in a given column or row is equal to the degree of the corresponding vertex. So it's an easy way. Adjacency matrices are very good for spotting immediately the degrees of vertices. You just add up the entries in a given row or column. So you can spot very quickly that a graph is regular if the sum of all the numbers in each row is the same. That would be the common vertex degree. So let me now give an example. Let's see, let's move on. Well, here I've said the same thing in symbols, namely we said that the vertex degree here is, this is really summing, well, here I'm summing, n is the number of vertices, and I'm summing over the columns. Remember, J normally represents the columns, so I'm just taking a given row, I'm fixing the row and summing the entries in that row by summing over the columns, and that's the vertex degree. That's the degree of the vertex corresponding to the row number. So that's just in symbols what I said before. Okay, moving on. I just want to very quickly give you a couple more definitions. This is slightly more advanced, but I think you should know about another square matrix which is related to any graph, and it's the so-called Laplacian. Well, normally we have to restrict to simple graphs here. So we suppose that we have a simple graph, G, as before with n vertices. And first of all, I define a diagonal matrix D, which is just the diagonal matrix of the vertex degrees. So I just put the degree of each vertex in the corresponding diagonal position. So in the original path graph, without the loop or the multiple edges, the multiple edge, I should say, the degrees were 1, 2, 2, 1. So in that case, the diagonal matrix D would be this diagonal matrix with zeros elsewhere, above and below the diagonal. So that would be the degree matrix. And then one defines a matrix capital L by taking D minus A, the degree matrix, which is diagonal, minus the adjacency matrix capital A. And this new matrix, it's again n by n matrix, is called the Laplacian matrix. It actually has something to do with the Laplacian in analysis. It's some sort of discrete version, but I can't go into that today. It's sometimes called the Kirchhoff matrix as well, of the graph. Now, the interesting thing about this matrix is that by the way it's constructed, the sum of its rows, if you think of each row as a vector, the sum of the rows is the zero vector. And that's because, just write down this, I won't do it now, but write down the matrix L in our path example. I've given you the original adjacency matrix we wrote down, and I've given you the diagonal matrix, so you can easily write down L, and you'll find that when you add up all the rows, you'll get the zero vector, or if you add up all the columns, the same thing. And that's because, you see, when you add up all the elements in a given column, you'll get the degree of that vertex, but that sum will be exactly cancelled by the diagonal entry you've put in capital D. So the sum of all the row vectors will be the zero row. And what that means is that the matrix L cannot be invertible because there's a linear relation between the rows or between the columns. Their sum is zero. So actually, more generally, we can deduce the following fact. So this is a theorem which you should know, but certainly you don't need to know the proof, but I think you should know the theorem. And this is, you can find this written in section actually 8.4 of the lecture notes. Namely, the rank of the Laplacian matrix L is actually n minus the number of components of the graph. So if the graph is connected, that means it has one component only. So the rank of L would be n minus 1. And that's as big as it could be, because I've already told you that the rows of L are not linearly independent. So its rank can never equal n. Another way of saying this is to say that the number of components of the graph is actually equal to the nullity, what's called the nullity of the matrix L. Or if you think of the matrix as defining a linear transformation from Rn to itself, this is the dimension of the kernel of that linear transformation. And the interest in this theorem is it's taking a concept from linear algebra and it's telling you something about the appearance of the graph. You can actually detect how many components there are, whether or not the graph is connected in particular, by looking at the rank of this matrix. So you should certainly know this result. The problem is that for complicated graphs, it's quite difficult to actually write down these matrices. They get quite complicated. But the theoretical result is interesting. Now, I still need to talk about, I'd like to talk about the so-called, something else you can get from the adjacency matrix, namely its characteristic polynomial. So we can also talk about the characteristic polynomial of a graph. So you see, the adjacency matrix, it does depend how you label the vertices of the graph. If you change the vertices, you'll get a different adjacency matrix. But changing the vertices will only permute the rows and columns of the graph. It's a bit like changing the basis when you think of the matrix as a linear transformation. So you'll just get in particular, you'll get a similar matrix, and many essential properties of the matrix don't change under that sort of transformation. Similar matrices have, for example, the same determinant, they have the same characteristic polynomial. So, well, I've also said here that if you have a graph that's not connected but has, say, two components, then if you choose the vertices carefully, first of all in the first component and then the first group in the first component, the latter group in the second, then you'll get an adjacency matrix in block form, which will make it easier to do calculations. But anyway, as regards the characteristic polynomial, I'd like to remind you of the definition of the characteristic polynomial for a matrix. If you have a square matrix, the characteristic polynomial is the determinant of that matrix. Well, at least my definition, I take the determinant of A minus x times the identity. That's the characteristic polynomial of a square matrix, and so if the matrix A is the adjacency matrix of a graph, that for me is that is by definition the characteristic polynomial of the graph. And the important thing is that if you have isomorphic graphs, they will have to have the same characteristic polynomial because they'll have the same adjacency properties. The vertices may be relabeled, but that will not change the characteristic polynomial. So if you want to detect different graphs, you can try and look at their characteristic polynomials. So I'd like to give you an example of this. We won't actually be computing characteristic polynomials, but it's important just to have an example to see how important this concept is. And so let me give you the example of what happens for our very simple path graph. And here is the characteristic polynomial of the path graph with 4 vertices. So it's all I had to do to get this is it's the determinant of A minus x times the identity. Well, we already did A at the beginning of the talk, so I just have to take minus x down the diagonal, and rather than zeros down the diagonal as before, and I take the determinant of that. Now it turns out that determinant, the roots of that determinant, it's equation of degree 4, are precisely plus or minus phi and psi, where phi is the golden ratio, which we've seen before in connection with Fibonacci numbers, and psi is the negative root of this polynomial. But we also get minus phi and minus psi, which are the roots of this factor here. In fact, had I ordered the vertices a bit differently, it would have been easier to see that this characteristic polynomial is of that form. If instead of ordering the vertices in the line 1, 2, 3, 4, I'd have ordered them 1, 3, 2, 4, I'd have got a matrix in block form, so it's worth doing that exercise. But anyway, we have the characteristic polynomial of our path graph, and you see we get these roots, which we've seen these numbers before. And these roots, these are the eigenvalues of the matrix, of the adjacency matrix, and they're also, you can also refer to them as the eigenvalues of the graph, because they do just depend upon the isomorphism class of the graph. Now you might guess this has got something to do with Fibonacci numbers, because you know the phi and psi are used to define in the formula for the Fibonacci numbers. And in fact, what happens in this case is if we take powers of the adjacency matrix A, we do get Fibonacci numbers. Any power, in fact, of our adjacency matrix A is a matrix consisting of a certain number of zeros, and the other numbers are Fibonacci. Well, 0 is also a Fibonacci number, but that's not the point. The other numbers are Fibonacci numbers. For example, a to the power 11 involves 55, 89, and 144, which are consecutive Fibonacci numbers. Let me explain what these entries represent, because this is another result which you should know about. Namely, it's not difficult to show. I'm not going to do it in this talk, but it's not difficult to show that when you have the power of an adjacency matrix, like a squared a to the 4th, for example, the entries of that matrix power are counting the number of walks For example, for a to the fourth, it would be walks of length 4. That means walks involving 4 steps, 4 edges, from from a given vertex to another vertex. So, for example, the 5 here, let me explain the 5. Why is there an entry 5 there? It turns out there are exactly 5 walks from vertex 2 to vertex 2, back to itself. So let me draw the path graph again, and I'll explain this. So here's the path graph, and we've labelled the vertices 1, 2, 3, 4. And there are exactly 5 walks of length 4 from vertex 2 to itself. So we're starting at vertex 2, and I've got to walk 4 steps and get back to 2. And the 5 possible walks are listed there, but let me just say pictorially. So think of these as sort of walking a dog or something. You go back and forwards. So you could go, remember, in a walk in a graph, there are no particular restrictions. You can go twice over the same edge. So I can go 2 to 1 to 2, and then back to 1 and back to 2. That's a walk with 4 steps. Or I could go 2 to 3, back to 3 and back to 2. That's another walk with 4 steps. These are the first 2. No, actually they're not. Sorry, these 2 are the ones that I've just done. Or I could, what else could I do? I could use both the vertices 1 and 3. So I just go 2 to 1 and then to 3 and then to 2, like that. Or I could go first of all 2 to 3 to 2 to 1 to 2. Okay, now I've got a total of 4. I've done these 4, and the only one that's missing, you've guessed it, is to go from 2, 3, 4, and then back through 3 to 2. So that's the total of the 5 walks from vertex 2 to vertex 2. And it's quite easy to show that each entry is what I've written in this proposition here, which you should know. If you've got a power, say a to the power k, shouldn't really use n because n is normally reserved for the number of vertices, which here is 4. If you have a matrix power, say a to the power k, then each entry in that matrix counts the number of walks with k steps from the relevant vertex to the other vertex, or if it's a diagonal entry from that vertex to itself. And you can prove this by induction using the sort of relation, using the formula for multiplying matrices. It's like a sort of big recurrence relation. In fact, of the sort we did when we looked at the counting the number of ways of, we had a network of one-way streets, and we were counting the number of ways of getting from a start vertex to a given vertex in that network. So that's another use of adjacency matrices. If you take powers of them, you get very quickly, you're counting the number of walks of a given number of steps from one vertex to another vertex. So that's a useful application. Okay, moving on. This is the last slide, and I'd like to talk about what are called directed graphs or digraphs. They are simply graphs as before, but each edge now should have an arrow. So each edge now becomes what's called directed. So what that means is that we can actually very usefully represent a digraph by means of an adjacency matrix, but this time it's no longer going to be a symmetric matrix. So the idea is that we'll assume the underlying graph is simple, or maybe it doesn't have to be, but we put a 1 if there is a directed edge from I to j. So if we have an edge from I to j with the arrow going from I to j, each edge is going to have an arrow now, then we denote Aij by 1. We could also have a loop, but we'd need to have an arrow on the loop. So that would mean Aii would be 1. So here's an example of an adjacency matrix and a digraph. Later on we'll be studying actually also graphs with numbers on each edge, so-called weighted graphs, and after that even with both numbers and arrows. But for the moment, here's an example of a graph, a digraph, which just has arrows on each edge. So it's an example which actually in the notes in 4.1 of the notes, but I haven't mentioned it before. So here is a matrix, an adjacency matrix. It's no longer symmetric, and it's giving information about a graph actually that comes from arithmetic, or if you like, from number theory. It has 8 vertices. It's an 8 by 8 matrix, 8 by 8, and we can, you don't see the edges because of the black, so I'll have to draw in the edges. But it turns out that here I've labelled the vertices 2 up to 9. So actually the first row corresponds to vertex 2, the second row to vertex 3, the third row to vertex 4, and so on, and similarly for the columns, because these are going to represent congruence classes for multiplication mod 11. And I'm forgetting about 1 and -1, which would be 10. I'm just using the congruence classes from 2 up to 9 inclusive to make sure the graph's connected, otherwise the graph wouldn't be connected. So, for example, 2 squared is 4, so that would be true always. So, so there's an arrow from, there's an edge from 2 to 4, and there's an arrow that goes from 2 to 4. If you can't see the numbers, this is 2, this is 4. And then 9 nines are 81. 81 is 4 mod 11, so there's also an edge and an arrow going that way. And in fact, we get a square of arrows like this. This is 4. 4 fours are 16, which is 5 mod 11. And so on. This is 3, this is 9, and this is 8. An arrow this way, an arrow this way from 7, and an arrow this way from 6. And that's consistency with the data in the adjacency matrix, because you see there should be an arrow from 2 to 4. That's what this 1 represents. There should be an arrow from 3 to 9. That's what this arrow represents, and so on. So you see that's probably, we don't use the adjacency matrix much, but we could have used it to define this graph here, which somehow represents quadratic ratios. What happens, quadratic residues, what happens when you square numbers modulo some other number. Okay, that's it for today. The next couple of videos are concerned with finding trees that span the vertices of a graph.